right, just a few minutes ago, I think you guys must heard a song, Just an Illusion. And today you are going to know that, well, the abstraction or say like the memory you see in your program is actually an illusion. But before we're talking about the memory illusion or say the virtual memory abstraction in your system, it's still worth a while to remind you guys where we were. So yesterday we are still on a big picture that right now you know that your memory is in a hierarchy, and whenever your processor wants to access memory, no matter it's instruction memory or data memory, it always has to go through the level one cache. So through the lower instruction, low store instruction, first of all, we have to contact L1 cache to see if we have the stuff we want. And if not, if the answer is yes, then that's a hit. The processor can continue execution. But how do we know it's a hit or not? First of all, you have to partition your address into tag, index, and offset. And we use the offset to identify the right word to output when you are requesting this address. And the index is to identify which set of blocks would contain the tag of the block that you are looking for. So if the tag has a match, then we know it's a hit. Otherwise, it's just a miss. So if it's a hit, we can have the L1 response to your processor and serve your request and continue execution. Otherwise, we will have to go to the lower level memory hierarchy. And when we want to go to lower level memory hierarchy, because we want to get the requesting block back into the label of the cache that's currently have the miss. So you have to make space for it. So to make space for it, you have to kick out an existing block that is currently in your cache. And the policy used here is least recently used policy for most of the time. And but when you kick out the block, there's no guarantee that the block is never modified. And if it's modified, given the fact that we always perform the update, the access only at the first level cache, it's highly likely that the L1 cache is the only guy who has the right content. So you have to write it back first. Otherwise, the stuff that you just modified would just get lost in the system. And then you will, after you write back, you can perform another search in L2. However, if the L2 still doesn't have the stuff you need, you have to repeat the same process as what you did in L1 again by write back if necessary and fetch the block you want from the lower level memory hierarchy until you find it. And you can return to where the miss occurs and finally got to the processor. So that's the process when we access the data. And last lecture, we talk about, well, it's problematic if we have a miss. And here are the source of cache misses. Compulsory misses, the first time we access a block. Capacity miss, the working set size of an application is bigger than a cache size, and you cannot fix this miss without increasing the cache capacity. And conflict miss, its required data block is presented in the cache before. However, it's replaced by another block that mapped to the same set before I use it again. So it's similar to the idea of collision in hash. However, the conflict miss, if you want to have a clear definition of it, is that some kind of miss doesn't go away even though you made the cache fully associated with. Well, so if you think, well, so some people would get confused about conflict miss and capacity miss because for capacity miss, there also exists the situation that, well, I want to access this data again. However, the data is just so big, right? So the trick is this: if the conflict miss doesn't go away, even though you made a cache fully associativity, means that the block can go anywhere. Then it's a capacity miss because we said the reason why we can have conflict miss is because they are competing with the same set. However, fully associativity means that the set is technically the whole block, the whole cache, right? So if it's still there, then it's a capacity miss. So these are three different distinctions of the miss. And here's a summary how we fix that. So as you can see, from the hardware perspective, you can increase the block size to reduce the compulsory miss. However, it will increase miss penalty. You can increase the weight associativity. However, it also has the side effect of increased hit time. You can increase the capacity. However, it has the drawback of more expensive hardware cost. So you can see like although hardware, if you change the hardware configuration, it will solve the problem. However, all of them have their own side effects. But on the other hand, if you look at the software part, they address each of the myths. However, there's no side effect. So what it tells you here is that in terms of these optimizations, if you can make your software to be aware of the fact that we have the hardware code cache in your processor to help you supplying data more smoothly, then you can potentially improve you can better use them to improve your performance without causing any side effects. So this is very important. So that's why computer scientists should learn the memory hierarchy very well, because that's actually a big part of your performance loss, as we just previously demonstrated. And you should remember that in a demo last lecture, we successfully used the block algorithm to improve the 2K by 2K matrix multiplication, reducing the time from 28 seconds to just 6 seconds. And if you are willing to do some extra work like matrix transpose, then you can further shrink 1 second out of it. So this is the summary of what we have learned. So now let's talk about virtual memory. So before we talk about virtual memory, I know a lot of you consider yourself as a good programmer. So right now I have these pieces of code. So if you understand C, you probably know that, well, for here I'm creating a process, and I create a random number. And when I create a process, then I should presumably have two concurrent programs run this. So and each of the process would generate a random number. So I'm curious to ask you, like, if I have two processes running concurrently, like this, can you project what's going to be the output and how many of the following statements here are correct? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your answers, it looks like we definitely need some kind of group discussion. So let me see. Okay, so right now I will give you about 2 to 3 minutes to discuss with your friends and make sure that you go into the breakout room. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now let's look at that. So right now, most of you think the answer is B. So I do want to invite some of you to share your thoughts with us. Okay, I have Twee. Okay, welcome back.
Thank you. I chose, well, Michael chose E, which is like the least popular answer because I think some instances might print the same value of A because it's random. So that might happen that the same value of A might be printed, but the address of A is different for each instance because it's different threads or processes running.
Okay, so is that what your group is thinking about?
Yeah, we chose E. So 2 and 4 we think are correct.
Okay, other objections, like what other people thought? Because like apparently this is not the most popular answer, right? what other people are thinking about. Then why you choose B? If you are not certain about your answer, why you chose B? All right, so let's have a demo, right? So what's the answer? So let's try to have a demo and let me show you this. So this would be CSE141 and virtualization. Okay, so this is the, so this is not the code of, but what if this? Is this the virtualization.c? No, okay, so they are the same. Okay, so for this program, right? So technically, we want to run like 2 instances of the same program, right? So the given code is using the process abstraction, but I don't think it matters that much. And as long as like for this example, I have 4 different processes, right? And let me show you this, right? So for virtualization, it tells you this is process A, B, C, and D, and the address is of A is what, and the value of A is what. So let's try to run it. Oops. Okay. Oh, because I haven't made that. Okay, here we go. So let's run it now. So first run, each program is each process is using different processor. The value is different. The address are all the same. The value of A is different and the address are all the same. Right, so that's the result. So if you look at that, right? Okay, Tweet.
I did see like 2 of the same values of A though. Does that matter?
Which
I know
two?
it's from like
Which?
that one. So the one A is using CPU 7 and
It's
that
the
one.
same.
It's the same one?
Same, right?
Okay.
Yeah, it's the same. It's printed. It's 2 statements printed from the same one, right? But no matter that, you should all agree that the address of A is all the same, right? Okay, so so if you look at a demo, you will figure out that, well, if you think, I do agree with you that in some cases, if you run it for many times, like if your number of total processes is really large, then it's highly possible that you are probably seeing the situation of 4, but most of the time it should be 5. Right, and but so 4 and 5, yes, but for the first one, the printed address of A is the same for every running instances. The printed address of A is the same for all running instances, right? So so now you know there's something. So why is that? So the reason is because we have the virtual memory abstraction, right? So the basic idea right now in our computer system is that we have so the first thing is that we have the virtual memory abstraction, and let me see what's a good slide. Okay, so the basic idea of virtual memory is like this. So my processor is living in an illusion that I am executing program on the virtual memory space. So when I am executing a program, I have to I have to go through this virtual memory space. So saying that if right now I am access instruction 0, and the virtual memory abstraction would dynamically remap this instruction 0 to somewhere in the memory, that may not be 0. And when I'm accessing data saying like this, it may also be mapped to somewhere in the memory. And for another program, another process, if my instruction is at 0, the 0 is actually a different 0 in the physical memory location. And if I'm accessing data, if like this address, it may also be mapped to a different location on the physical memory. So that's the idea of virtual memory, is that we create an illusion that everyone owns a complete 32-bit or 64-bit memory address space. However, the virtual memory abstraction dynamically remap your physical location with this virtual address. So that's the whole idea of virtual memory. So right now, I want you to think about what's the good thing about having such an abstraction called virtual memory. All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what you guys showed here. Okay, give me a second. Okay, I just sent out the discussion question because if you look at your discussion result, it looks like we definitely need some kind of conversation between you and your friends. So why don't we just, start doing that? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you guys, looks like you guys still like the answer of C. So why don't we just have some of you tells us why you think two of them are correct, and maybe I could select a few of you and you will figure out that the two that you guys are thinking may be different. All right, I have Tui. Okay, thanks for clarifying our misunderstanding.
So I'm pretty sure everyone thinks 3 and 4 will happen because that's what my group mates think also.
But why is the case?
Because I think in the book they said something about how like overlaying or overloading. I don't remember the
Well,
correct term.
don't need to go that deep, right? Like think about like if I just expose the physical memory location to you, and if the program is like just like what I show you, like everyone's A is associated with the same memory address physically, then what would happen?
It means that other programs can modify, one program can modify other programs' data
Right.
if they
And that's
wish.
one thing, right? And then, well, they may not be able to run simultaneously because one program may accidentally terminate the other one, right? Okay, so 3 and 4, you agree with that. But
And
anything
I also
else in
think
your
2 is
mind?
correct, but I
2
don't
is
know if
correct.
1 is correct or not. I'm unsure about 1.
Okay, why do you think 2 is correct?
I think 2 is correct is because if you map a program's address to the actual physical address, if you run it on a different machine, even if they have the same processor but different memory capacities, it might exceed, or it might exceed
Yeah,
like the
so
next. Yeah,
that's
you
a
know what I
basic
mean.
thing, right? So like if I'm rich, I have like, let's say it's like 64 gigabyte of memory on my machine, and I had just had a program that can use out all the 64 gigabyte of the physical memory, right? Can this program, and if the program has to run in physical memory space, then this program won't be able to run on a machine with less than that memory, right? So 2 is correct. How about the first one?
I'm not sure about the part that is cannot
Well, so think
exceed.
about what I just said, right? If you are going to use more than if you can only interact with physical memory, right? Can you ever use more than that?
No, you can't. But I wasn't sure if
Right.
virtual memory can be bigger than physical memory or not.
So, right. But at least if you can only use physical memory, this is also an issue, right? Right. So everything here is actually correct. And let me show you, and thanks for your insights, right? So let me show you what will happen. So if you expose the memory directly to the processor, what will happen is that, okay, first of all, if I have one program that like this, well, if it fits in the memory, it can run. But if the program is bigger, right, the additional place, there's no place to fit in the additional data, right? So one, it won't work, right? So the second case is like this. So I have a program, it used the memory very well. However, if my memory is small, if I am moving this program to another machine with smaller memory, then it won't work, right? Third, if I have two programs, if I launch the first program, say Chrome first, right? But if both program needs the physical location, then they cannot both fit in the memory, right? They cannot both fit in the memory because your capacity is limited if you can only use physical memory. So if you look at this, everything here is correct. And that's why we have the virtual memory abstraction by assuming that everyone is running in a virtual memory space, and all the programmer and all the processors see is the virtual memory space. And the system side, including the computer architecture and the operating system, will handle this manipulation between the usage of virtual memory and the physical memory locations. So that's a basic idea of virtual memory. So virtual memory is an abstraction of memory space available for programs and software, or say programmers. Programs will execute only using the virtual memory addresses, and the operating system and hardware will work together to handle the mapping. And like I said, in cache, the cache architecture, they consider the whole memory space as in blocks. And virtual memory consider the whole memory locations into pages. So the virtual memory scheme that we are using right now is called demand paging. So the basic idea of demand paging is that each program, each process, they would own their own page table. So when I am, and it's called demand because it only trigger the mapping between virtual address and a physical location on demand. By on demand, we say your program is trying to use it. So say like right now, the Chrome needs its instruction 0. Then the virtual memory abstraction would map the page table of virtual address 0 to somewhere in the physical memory location. And the operating system would be responsible for loading that part of program from storage to the physical memory place. And if you are accessing data, we are also doing the same. The page table must create an entry for the requesting address and load it from the storage to the memory. And if you are doing another process, then even though the address, they are both 0, however, it will be mapped to a different physical location and from a different original location in your storage, or maybe the same if they are the same program, right? However, because it's different instances, they will have to use different memory location. And gradually, you will use the memory, you probably will fill out the memory location. However, the magic here is that if I use out all my physical memory location, I can just use LRU policy to spare a physical memory location for the requesting block like this. So this concept is like demand paging. And you will feel like this has some flavor as cache we just said. So the demand paging is actually treating the virtual memory as your virtual memory abstraction as your real memory, and the physical memory, which we use DRAM to build here, is actually a cache of your virtual memory. And the page table would be something like a mix of your tag array of your content in your physical memory. So that's the basic idea of demand paging. So if you look at the virtual memory abstraction, then it will be like this. So first of all, we partition the address space into pages. And whenever I need to access, I will consult the page table. And the page table would tell me where in, if the address that I'm requesting is currently on map, the page table will find a place in the memory to accommodate that page so that your processor will be able to find that page. So that's the basic idea of virtual memory abstraction. So if you keep this in mind, right, you will figure out that the previous demo, because we are creating two processes of the same program. So each program, each process, they would have a different page table. So even though their address of A seems to be the same after the print out, however, it will be going redirect to different page tables, and each page table will have their own mapping between this virtual address abstraction and the physical memory location. So that's the whole idea of virtual memory. And thinking about the address translation in virtual memory. The whole thing is that you need a page table, as we just mentioned. And the program will receive the processor instruction would use virtual addresses from the running code. And the main memory is the physical address. And what you will have to do is that you need a page. So whenever you need to access the data or instruction, you will partition your address into page offset, meaning the location of the requesting word within a page. And the rest of them will be the virtual page number. So you use that virtual page number to access the page table to look up your physical page number, which tells you where in the physical, which page in the physical memory contains your requesting data. And the page offset, because we every time when we bring in data in the main memory, it's on a page granularity based. So the page offset will never change before and after translation. So that's how the address translation in virtual memory abstraction is made. So, and previously we demonstrated the idea of demand paging. As I said, the demand paging is treating the physical memory as a cache of your virtual memory. And you may consider the analogy like this: the block size is like the page size, and the page table is like the tag array. And unlike the cache we are making in set associativity, it's a fully associated cache because a virtual memory page can go anywhere in a physical main memory. So that's the idea of virtual memory. And as you know, well, it's the soul of virtual memory is that you have to maintain a page table. So right now, I'm inviting you to think about how big the page table is in modern 64-bit architectures. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your answers, I believe we definitely need some kind of discussion, and I already sent the question out. So go ahead and discuss it. And if you don't go into your designated room within 20 seconds, I will deduct your participation points. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, the answer is like this. And we have some of you, we have most of you think it's B, but also quite a few of you think it's D. So can I have some of you sharing your thoughts? Okay, I still have Twee. Okay, you are my best friend, being honest.
I'm sorry. So I chose D, but it really was like
Uh-huh.
255. 2 to the
So how
power
do
of
you get
55.
D? Yeah, but yeah, how do you get that?
So for number of page table entries, you take 2 to the power of 64 because you're working on a 64-bit virtual address space, divided by 2 to the 12 because that's your page is 4 kilobytes. So then you get 252, and then you multiply that by the size of each table entries, which is 2 to the 3. Yeah,
So that will be 2 to the 55, right? So
yeah.
it's basically like 2 to the 5 petabytes,
Mhm.
right? So how many of you have petabytes of memory? You don't have petabytes of memory, right? So thanks, Twee. So, but the issue is that if you look at the size of the patch table, right? If you are using the 64-bit virtual address space, you need such a big page table. Just the page table is even bigger than your physical memory. So if you didn't like tweak your page table carefully, it's not going to work, right? So, and as I said, if you have issues with this, right, CSE140 is your best friend, and I don't know who's offering, but definitely a class that you should take. So, but the thing is that, do we really need a large page table, right? So let's think about if you remember what we have been talking about in the memory abstraction, right? So when we run our program, right, your code and static data start from the beginning. The code is like your instructions, and the static data is like the global variables. And when you are running your program, we gradually grow the memory address space from the beginning and the very end. From the beginning is the heap. So if you try to do things like mallocate, your memory would go from the beginning of the heap, which is the right after the end of your static data. And if you are trying to use like if you try to do function code, it's going from the end of the stack, which you should already know when we talk about the instruction set architecture. So if you look at that, when you start running program, it's usually like the very beginning part is used. The very end part is also used, right? However, you probably would never use the middle part. So actually what you really need to know, what really you really need is probably just have sufficient amount of entries in the very beginning, but not in the middle, right? So here is the modern page table design, is that we make the page table a tree structure in a way that it's I would say it's like a B plus tree or something, right? So in each level of the node, you contain a few hundreds of entries, and this a few hundreds of entries, your virtual address will first map to the first level of the tree, which is part of the a few hundred level of entries. And this a few hundred of entries, they will further map to other subtrees of your page table. But as you can see, the middle part, because you are not using, so this part, they will not create subtrees of the page table. So in this way, you can reduce the amount of entries that you need. So let me walk through an example for you. In modern x86 architecture, there is a register, spatial register in the processor that points to the root node of a page table of the running process. And each page table node, they contain 512 entries. So the CR3, the register we point out would point to the root node of the tree of the page table. And in modern x86 64 architecture, they are actually cheating because they are not actually using the complete 64 bits. They only use the 48 bits in their address, and for the the most significant 16 bits, they are only sign extension. So you think you are using a 64-bit address space. However, in modern x86 architecture, it's only 48 bits. But that's set that aside. So within this 48 bits, the the topmost or say the most significant 9 bits will be used as the index for the one of the 512 entries in a root node. And if the address is used before, then it will create a subtree which you can use the pointer in this entry to go to the root node of the subtree. And again, this root node of a subtree is also a node with 512 entries. So where do I know? How do I know? How do I know the next level of the subtree should I go to? Use another 9 bits, and you will find out. And gradually, you will find out the last level entry in your page table. That will give you the physical page number and concatenate that with your page offset. That's how you get your final address of your memory location. So this is how we reach the physical memory location in x86 64 architecture. And that's common in many of the computer architecture right now. So right now I'm having you thinking about this question. Now we have virtual memory, but if I have a move instruction like this, how many memory accesses do we need? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so this is your answer, but I do believe you guys really need a discussion because, you know, most of the time, the first one is not correct. So let's go. right. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so, well, so now most of you think it's B, but C is also a popular answer, and 2 of you think it's E. So can I have some of you share your thoughts with us? Okay, I have 2E.
I'm okay with being the lamb.
Okay, only you.
But
Only you. All right.
I chose B because it's just based on what you showed from the slide before is
Okay,
first.
so are you sure it's only 4 in this case?
I'm not sure at all. It's just based
Right.
on.
So this is 1, 2, 3, 4, right? But that's
Mhm.
only getting you the address, right?
Mhm.
So I also need to get the data, right?
Mhm.
So in this way, what?
Is it 6 then?
1, 2, 3, 4, 5, right?
Mhm.
So, but you guys chose even 4 or 6, right?
Mhm.
So the truth is that, right? Don't forget an instruction
Oh
itself
yeah.
has two memory accesses, right? Instruction itself is also in a memory.
Mhm.
So an instruction also lives in virtual memory abstraction. So you need a total of 10.
Okay. That makes sense. Thank you.
All right. So don't forget, this is von Neumann computer, instructions, data, they all live in a virtual memory abstraction. All right. So now, if you look at this one, the answer is actually E instead of B, C, D, right? Because don't forget, instruction itself is also in the memory. Okay, so right now you see, well, first of all, page table is so huge, right? And even though we use the tree, you still need to walk many of the entries, right? So the address translation is actually indeed a big overhead. So how can we avoid or say like improve this overhead? So the solution, the architectural solution here is that we add something called translation look aside buffer called TLB. So TLB is not a sandwich, it's TLB. The sandwich is BLT, right? So TLB is a small SRAM stores frequently used page table entries. So what happened is that, okay, right now my processor issued this request and the TLB would translate it to the address that you are looking for and use that to search for your cache, right? So that's the basic idea of TLB. So the good thing is that it's a lot faster than having every traffic going to the page table in the DRAM. However, you are making your hit time longer because every time when you access the L1 cache, you still you will add the overhead of accessing the TLB. So, and the issue here is because your L1 cache is using the physical memory, right? So another thought is that what if I make the L1 under accept virtual addresses? So what will happen is that when I have a request, I just send them together in the meantime for both uh, lookup and in a cache and a TLB. So if it's a hit, then I don't need to go to the, I don't need to, if it's a hit, then I just pay the same amount of overhead as I paid before. If it's a miss, then I just simply use the translated address to access L2. So that was the thought. However, as the demo we just showed you, right? Many applications have the same virtual address, like my A and your A, they are the same. If I am running two programs concurrently, how do I distinguish whose A is that, right? And another thing which is even worse, right? Even within the same application, right? There could be an alias of virtual addresses that they are physically the same physical location. And if you have two virtual memory addresses that are pointing to the same physical location, you are going to create two different entries in a cache. First of all, you are wasting space. The second thing, which is the worst thing, is that they are not synchronized. So you will have two different copies of the same data. So both are not desired. So this solution looks good, however, it doesn't work. So it cannot be looks like this. So what's our solution? What's our solution, right? So the key thing is that you have to use physical address to judge if that's exactly what you want, as we said, right? To tell them if they are the same, physical address is actually the key. So the real solution we have right now is called virtually indexed, physically tagged cache. So the basic idea of virtually indexed, physically tagged cache is like this. The page offset, as we mentioned, is never translated in, it's never translated. And the virtual page number and the physical page number are the ones that will change after translation. So the basic idea of the virtually indexed physically tagged cache is that can we use the virtual address to index the potential data location in the cache? And to do that, the only thing that is not changing is your page offset. So the basic idea of virtually indexed physically tagged cache is that we use part of the page offset as our block offset. We use part of the page offset, the other part of our page offset as the set index, since they never change before and after translation. So if it's equivalent if you use the set index in the virtual address and a physical address in your set index to access the cache. And physically tagged cache means that the tag array that I store in my cache is actually the physical address. So what to do here? So this is the tag, right? It's in a physical address, right? So what will happen here is that if you make your cache like this, when you have an address coming in, again, partition the address into block offset, set index, and the virtual page number, because this is virtual address. And the set index is used to identify which set may contain my block. And the virtual page number would be used concurrently in a TLB to find out the physical page number of the requesting virtual page number. And because your page offset is equivalent to the number of bits of your set index and block offset. The physical page number is actually going to be the tag in your cache. So if they match, it's going to be a hit. And as you can see, because these two parts, they are performing concurrently. So you get a benefit of virtual cache. On the other hand, because the tag and is used physical page number, so you also get the benefit of using physical address to access your cache. So that's a virtually indexed, physically tagged cache. However, it does give us some constraints about how big your cache is. So for example, if a page size is 4 kilobytes, which is the most popular page size in modern systems, then we know that for the set index and block offset, they must fit in a page offset. And remember, as what I said, the log B is the block offset. Log S is the page offset. Sorry, the set index. So log B plus log S, they must fit in the page offset, which is 12. So if you use C equal to ABS, you will know that C must be equal to A times 2 to the 12. So if you only have a direct map cache, meaning that your A equal to 1, your cache size can only be 4 kilobytes. So that's the constraint of virtually indexed, physically tagged cache. So right now, I am inviting you to think through this question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so why don't you guys go ahead and discuss with your friend for another 2 or 3 minutes. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, looks like B is a popular answer. So can I have some of you explain how did you derive your answer? How did you get there? Okay, Tui. Are you the only one who had a conversation with me today?
I'm sorry.
No, you don't have to say sorry. You saved everybody. Otherwise, we would just, stay until somebody, had his or her voice. Okay, what do you think?
Um, I really don't know because to me it seems like all of these were possible based on the previous
Why?
page. Because if it's an operating system using 4K pages, for
Mm-hmm.
A, if it's two-way, then A is 2 in the C equals ABS. So
Okay,
so then it's just 8 kilobytes, and that's still within the capacity. So that's possible.
no.
Or I don't know what B has to do with it, like 32
So
bytes plus.
it has to be exactly 12, right?
Mm-hmm.
Okay, so if you look at this, okay, so if for the first one, let's use C equal to ABS, right?
Mm-hmm.
So for the first one, what's the S?
32. I don't know how to calculate by doing this.
It
Sorry.
will be 512, right? So for C equal to ABS, right? So it will be 32 times 2 to the 10 equals to 2 times 2 to the 5, right?
Mm-hmm.
And
Mm-hmm.
times S, right? So this part is canceled. So this is 512, right? So
Okay.
how about this one? What's the S of it? So
Um.
that one is similar to the previous one, except
So.
for
It,
the A right now is 4, right? So you
mm-hmm.
will get an S of 256, right?
Mm-hmm.
And for this one, what's the S? So this would be C 32 times 2 to the 10 equal to 4 times 2 to the 6,
6.
and S is unknown, right?
Mm-hmm.
But we know this part has a 2 to the 5 here, so this part has a 2 to the 3, so this S is 128, right?
Mm-hmm.
And this S is 64, right?
64.
So what's the log B here?
Log B here is 5.
And what's the log B here?
6.
6. Okay, so what's the log S?
Um, I think that's 8 or 7. I don't remember.
9, right?
9. Yeah.
That's 9, right? So if 5 plus 9, is it
14.
so that one is not possible,
Mm-hmm.
right? Because it's more than 12. How about
Mm-hmm.
this one? This one is 5 plus 8,
8.
right?
13.
Right? So it's not possible, right? So
Mm-hmm.
this one is 6 plus, this is what?
7. 7.
7, right? That's 13. So that's also not possible, right? For
Mm-hmm.
this one is 6 plus 6 is 12. So that's the only one that's possible,
Okay, that makes sense now. Thank you.
right? So the most important equation that you have to memorize to remember in the whole memory hierarchy section is C equal to ABS. All right. And if you look at the design of this cache configuration, it's exactly how Intel structured their first level cache. So the first level cache configuration of Intel processor is always 32 kilobyte, 8-way, 64 byte. This is like a golden number, magic number. And this is, there's no other reason than because they want to make it virtually indexed, physically tagged to improve the performance of address translation. So sometimes you might want to ask me like, okay, why our L1 cache size is always so limited? And here is the truth. It's because we have to support the virtual memory abstraction properly, and the virtual and for the most important architectural support in doing this is the TLB, and the TLB uh, and because of that, right? Because of TLB translation, so the cache size is also limited. So that's the reason why your L1 cache configuration always look like that. All right. So now, before you leave the classroom, there are a few things I want to let you know. So first of all, assignment 4 is up on the website, and DA has a discussion session today, I believe, at 5. So if you are interested about like, okay, what's the tip of solving my assignments, that's probably the best place to start with. And some of you asked about the final exam on Piazza, and I think it's a really good time to talk about that. So the final exam will be on September 4th, and some of you requesting that, well, because I'm in a different time zone, because I am taking a job. Okay, so here's what I'm going to do. So we are going to open a test between 8 a.m. and 6 p.m. And you can choose any consecutive nonstop 3-hour slot with that ends at before 6 p.m. So saying that if I open the test at 9 a.m., so you have 3 hours from 9 a.m., which means that you need to submit the test before 12 p.m. And if you start it at 3 p.m., you have to submit it sharp at 6 p.m. And for some reason, if you get yourself late, like I start at 4:30, unfortunately, you still have to submit before 6 p.m. to receive your grades. So make sure you have sufficient amount of consecutive 3-hour slots on that date to have the final exam. However, unlike the midterm this time, we have the Zoom. This time we cannot do Zoom because I'm not going to be able to like, watch you guys like 6 a.m. to like 8 a.m. to 6 p.m. That's 10 hours. It's too much for me, right? So so what we are going to do is that I'm going to test out the lockdown browser, which means that once you use that browser, you won't be able to uh, uh, to switch windows. So which means that if you are using an online textbook, you probably need to find another device for that. And the as it's open book, open notes, but some of you already told me that the length of the midterm is good enough for you to not having time open the book and notes. So, and I'm saying like this time because it's a final and it's cumulative, it's covering all the materials from the first lecture to the last lecture in the next week. So it's going to be twice longer than a midterm, which means that you also have no time to open book, open notes. So although I say it's open book and open notes, but the test itself is not designed for you to have sufficient amount of time to open book, open notes. So so that's the thing. Other than that, I would wish you have a great rest